Welcome back to the Mathematician's podcast. I'm your host, Benjamin Cornish, and today we are squaring off against an ancient problem and circling back to the man who solved it, or at least for a given definition of solved. Mrs. Cornish and I got married back in 2018, and due to budgetary reasons with a minor element of arrogance, we opted for the DIY wedding. This was before I was qualified as a project manager, a certification I'm sure I will do one of these days. The entire affair was a shambles, which is just as well given our theme was farmyard chic. Let me paint you a picture. She has 26 cousins, half of whom will not sit next to the other half, and I only had a small family of 3, my brother, who obviously was not invited due to his devotion to conspiracy theories and his inability to enter a church as a result. However, my 2 remaining family members are staunchly conservative with regard to wedding tradition and demanded a bride and groom side of the church. This meant we were required to find a building that had an aisle running down all but the far left side of the wall. For dinner, we had 13 vegans, 11 pescatarians, 7 gluten intolerants, 5 nut allergies, and 3 people who exclusively ate food from their country of origin, which mainly comprised dairy, fish, and peanuts. But the tables could either be set to 6, 8, or 10, so it was impossible to separate them accordingly. The venue had a minimum deposit at the bar of a few grand, although everyone except my wife and I were teetotal. By tradition, we chose to have the ceremony in my wife's town of birth in Devon, and to save money, we were offered the use of my friend's stately home in Norfolk. But the carriage driver would only allow us to use the horses for a maximum of 25 miles, which meant making use of the numerous stables across the country to change the horses en route. We had several weeks of disagreement over the surname to choose, or whether we go double-barrelled. Fortunately enough, growing up in the same small town in Dorset, we were actually both called Cornish, although we did narrowly avoid being called Cornish. For the wedding bands, she wanted 3 colours of yellow gold, white gold, and rose gold. But I wanted them to match the heraldry from my Italian side of the family, which is in the Borromean style. But the jeweller refused and offered us Russian bands instead. During this planning stage, I had so many plates that I was trying to keep spinning, because this was also whilst I was at Clown College trying to secure a qualification to keep the future Mrs. Cornish in the lifestyle to which she'd become accustomed. As I say, it was a mess. So there we are. Still at the planning stage, a mere 3 years away from the happy day itself. How do we solve this problem? Well, we chose to elope. There was no way we were going to overcome all the obstacles and requirements that were placed upon us by society, geography, our family, and of course, Euclidean geometry. In the end, we ran off to the Maldives to get married and were witnessed by a couple of dolphins. So here's the philosophical question. Did we solve the problem? And in what sense was it solved? We didn't untangle any of the issues that faced us, or find the magic silver bullet that would cut through the nonsense. We just decided to nope out and avoid those rules. On the other hand, we got the job done, and at the time of recording, we have had a very happy marriage for 6 years and counting. I suppose it's a bit like Dinostratus in a way, which is convenient as he is the mathematician who we'll be focusing on today. Dinostratus lived in ancient Greece during the 4th century BCE. He was a student of Plato's Academy, along with his brother Menechmus, as well as Eudoxus, Theaetetus, and Theodorus, a part of the rich intellectual environment that birthed so many mathematical legends, and the last few episodes of my podcast. But Dinostratus is best known for something specific: his use of the Quadratrix to tackle the ancient problem of squaring the circle. Don't worry if you're already scratching your head, we'll unravel this soon enough. For now, think of Dinostratus as the underappreciated middle sibling of Greek mathematics. He didn't achieve as much as the others, but his work bridged a gap that the others could not. That said, Dinostratus wasn't all work and no play. he had a keen interest in philosophy, astronomy, and perhaps even engineering, although sadly there is little evidence of any progress he made in these fields lasting until the present day. Now let's circle back to the mathematical problem that made Dinostratus famous: squaring the circle. No mean feat this. It was one of the three great problems of Greek mathematics, alongside trisecting an angle and doubling a cube. The goal was to construct a square with the same area as a given circle using only a straight edge and compass. The Greeks loved a challenge, but they also loved rules. Straight edge and compass constructions were their version of the non-calculator exam. It really proves you know your stuff. Dinostratus' contribution to this problem involved a curve called the Quadratrix, originally described by Hippias of Elis back in episode 7. The quadratrix is a curve generated by the uniform motion of a line segment rotating about one axis, while another moves linearly along a perpendicular axis with a trace on the intersection of these two segments. This description leaves a lot for the imagination, so perhaps I could take a small tangent and talk about coordinate geometry. When we learn coordinate geometry in school, we look at values of x and y forming coordinates, which point to a position on an xy plane. This is normally called the Cartesian plane, as it was developed by friend of the podcast, René Descartes, in 1637. When we get to college, we then learn that coordinate geometry isn't just for coordinates. We can also plot functions, usually of the form f of x equals y, that connect the x and y coordinate to form a, hopefully, continuous curve. But then, when we arrive at university, we learn that x and y are just one option of a coordinate system, and in fact, any pair of orthogonal directions will do. Most famously, you may have heard of polar coordinates, r theta, where we measure a point by an angle from the eastern line and a distance from the centre. This allows us to construct beautiful curves with simplicity, in a way that would be significantly harder using Cartesian coordinates. For instance, r equals theta is the function that constructs the Archimedean spiral, more on that in a future episode. However, that particular spiral is impossible to construct in the y equals f of x notation, because it doesn't produce a function in x and y, and so we have to use significantly more complicated implicit functions. Well, how about we blend these two systems then, and measure each point by an angle from the eastern line and a distance vertically above the eastern line. So each coordinate then is y theta. I might point out here that I keep referencing the eastern line, as in the cardinal directions north, east, south, west, and that's because I'm trying to frame it not in the terms of the x-axis, although in this case east would refer to the positive x-axis. Similarly, you might want to describe east as the positive real axis in a complex coordinate system, but to cut through the mathematical jargon, I'm just calling it east, because we all know which way east goes. Here we have two arms described above, so one that is rotating and one that is translating. Our equation then to draw the quadratrix would be y equals 2 theta over pi. As the height increases, the angle increases at a constant rate. A little side note here, as this part of the script writing took me a hot minute to calculate, I used the software GeoGebra to design my quadratrix as the intersection of two lines, one radial, one horizontal, that both move with relation to a parameter t, and I then found the intersection of these two lines and set a trace on that point, which means it would draw the line made by the point as t varies with y equals 1 take away t and y equals tan of pi over 2 times 1 take away t x. Then I used a little bit of parametric equations to convert that into a y equals f of x curve, which yields y equals tan of pi y over 2 times x, at which point we can divide through on both sides by x to have y over x equals tan of pi over 2y. And then, if we take an inverse tan, we notice that the left-hand side becomes theta, that is the arc tan of y over x, because tan theta is y over x. And so rearranging this, we then have y equals 2 theta over pi. And from this version of the curve, it's perhaps easier to see how the angle is trisected back in episode 7 by Hippias of Elis, because any proportional division of y will also be a proportional division of theta. But back to today's mathematician, using the Quadratrix. Dinostratus was able to approximate a solution of squaring the circle. Now, it's not immediately obvious how the curve y equals 2 theta over pi can help with this. If we substitute back in tan theta equals y over x and rearrange for x, then we arrive at x equals 2 theta over pi times cot theta, which, if we take a limit as theta tends to 0, we get x equals 2 over pi as theta over cot theta tends to 1. While it wasn't a pure straight edge and compass method, and he certainly didn't use the analytical methods described above, it was a stroke of genius, and a bit of a curveball for his contemporaries. Let's unpack the Quadratrix again and explain exactly how Dinostratus used it to approach the ancient problem of squaring the circle. So, to square the circle, the goal is to construct a square whose area is equal to that of a given circle, with radius r. The area of the circle is pi r squared, so the square must have a side length, s equals r square root pi. The challenge arises because the square root of pi, like pi itself, cannot be constructed using only a straight edge and compass. But with the Quadratrix, Dinostratus could approximate this length geometrically. Here's how. Curiously, for this derivation, we will not start with a circle, but a square. But the area we will attempt to find the quadrature of, that is, a square of equal area, is the quarter circle inscribed within this square. If we set our compass at the corner of the square and describe an arc from one edge to another, this will be a quarter circle with area pi over 4. If we let this arc be the basis of our Quadratrix, along with the vertical line of the square, we can then draw another curve meeting the base at 2 over pi, as described above. The fraction 2 over pi is tantalizingly close to expressing pi as a length, but we do need to reciprocate it. Fortunately for Dinostratus, this is a fairly basic manoeuvre using similar triangles. Drop a perpendicular of length 1 and another perpendicular at the edge of the square and connect these with a triangle where one corner is the original square. We then have the proportional ratio of 2 over pi to 1 is equal to 1 to k, where this new length k must then be pi over 2. At this point, we can form a rectangle of the desired area by extending a perpendicular of length 1/2. So now we have a rectangle with lengths pi over 2 and 1 over 2. Here, we can make use of the property of the geometric mean. That is, the geometric mean of a and b is the square root of a times b. The ancient Greeks knew how to do this easily with geometry. Construct a semicircle of diameter a plus b, then construct a perpendicular at the point where a and b meet. The distance between this point and where the perpendicular meets the semicircle, then, is the geometric mean. For Dinostratus, this gives a length of the square root of pi over 2. Now this can be the side length of a square, giving an area pi over 4, which matches the original quarter circle. Oh, yes! Admittedly, this is only squaring a quarter circle, not squaring a full circle, but you can multiply them both by 4 and you're golden. The Quadratrix allows transformations between linear and angular measurements, effectively breaking the strict rule of straight edge and compass constructions. This is because the curve itself is not constructible using these tools. It's a more advanced construction. By intersecting the Quadratrix with other geometric figures, Dinostratus could access lengths and proportions otherwise inaccessible in classical constructions. It's worth noting that while this method provides a clever solution, it doesn't adhere to the strict straight edge and compass constraints of Greek geometry. From a modern viewpoint, we know that squaring the circle is impossible because pi is transcendental. We spoke about this in episode 13 on Theaetetus. The Quadratrix doesn't evade this fundamental limitation. It approximates solutions but cannot resolve the transcendence of pi. Even in my analytical derivation, I used limits to justify the value. And in that sense, at a limit, it becomes true, but it's never really true at any particular point. However, Dinostratus' method represents an ingenious workaround and a leap in mathematical thinking. By repurposing curves like the Quadratrix, he expanded the toolbox of geometry, setting a precedent for later developments such as those in trigonometry and calculus. You could say that Dinostratus didn't quite solve the problem, but gave it a new angle. Dinostratus wasn't just a mathematician. He had interests that spanned multiple disciplines, including astronomy and engineering. Some historians believe he contributed to early studies of planetary motion, building on the work of Eudoxus. It's worth noting that Dinostratus lived during a time when the lines between disciplines were blurrier than a poorly drawn Quadratrix. Philosophy, mathematics, and natural science were all considered parts of a unified quest for knowledge. Combining the ways of thinking in this time was tricky, like constructing a Quadratrix, but he certainly connected the dots. Legend has it that Dinostratus also dabbled in practical engineering, though details are scant. It wouldn't be surprising, many Greek mathematicians, including Archimedes, had practical streaks. If Dinostratus did turn his hand to building, it would explain why his mathematical curves seemed so well constructed. Dinostratus' work with the Quadratrix didn't just solve one problem, it struck a chord with ancient geometry and threw open the doors of construction. Suddenly, we can create shapes that do not rely solely on a compass and straightedge. What new tools, then, may be discovered? I'm sure we will ask Archimedes and Apollonius this question soon. When you study integrals and derivatives in high school, remember that these ideas didn't spring fully formed from Newton and Leibniz's head. Everything is built on everything else. But sometimes, ideas like calculus require a new tool that no one has used before, or perhaps a tool that can be repurposed in a different field. For calculus, this was the limit. For ancient geometry, this was the non-circular curve. In modern times, the Quadratrix finds applications in fields like computer graphics and robotics, where complex curves are essential. Think about those machines on the assembly lines that rotate and translate in all sorts of funky directions. You could say Dinostratus was helping to engineer the future. Let's revisit the problem of squaring the circle from a modern perspective. In 1882, Ferdinand von Liedemann proved that pi is transcendental, meaning it cannot be expressed as the root of any non-zero polynomial equation with rational coefficients. This definitively proved that squaring the circle using only a straight edge and compass is impossible. However, Dinostratus' approach remains valuable. His willingness to look beyond traditional methods reflects the spirit of innovation that drives mathematics today. Whether we are studying fractals, exploring non-Euclidean geometry, or simulating physics, we owe a debt to thinkers like him who dared to bend the rules. It's easy to think of mathematicians as solitary figures, scrabbling equations in darkened rooms. But Dinostratus lived in a vibrant intellectual community. He likely debated ideas over meals, exchanged notes with contemporaries, and yes, probably got into a few heated arguments about the finer points of geometry. In many ways, Dinostratus reminds us that maths is a deeply human endeavour. It's about curiosity, persistence, and sometimes failing spectacularly before stumbling on a breakthrough. And sometimes it's about going your own way, in spite of the world around you. As we wrap up today's episode, let's take a moment to appreciate Dinostratus, not just for his mathematical insights, but his willingness to think differently. So the next time you're stuck on a tricky maths problem, or trying to figure out why your pizza slices aren't evenly divided, think of Dinostratus. He'd probably tell you to keep at it, and maybe draw a curve or two. Well, thank you for joining me on this journey through the life and legacy of Dinostratus. Don't forget to subscribe to the Mathematician's podcast for more detailed discussions about the key figures who shaped our world. And you can also follow the pod on Blue Sky at mathematicians-pod for all of my off-topic musings. Next week, we will be going full throttle with Aristotle. It would be a logical move to tune in. Until then, goodbye! The music today is Danse Macabre Finale by Kevin MacLeod. You can find more information in the show notes.